Hydrogenation is an exothermic reaction, and it usually requires a solid catalyst and a high hydrogen pressure. The catalysts used in hydrogenation are platinum, palladium, or nickel. For example, the hydrogenation of 2-methylpropene requires a nickel catalyst and 50 atmosphere pressure of hydrogen. The role of the catalyst in this reaction is to absorb hydrogen and alkene onto the surface of the metal. The adsorption of hydrogen is accompanied by a pairing of hydrogen electrons with the electrons on the surface of the metal. Therefore, the hydrogen-hydrogen bond is loosened, and single hydrogen atoms can migrate to the adsorbed alkene molecule. When bromine is added dropwise to a solution of an alkene in a non-polar solvent, the dark red color of bromine disappears almost immediately upon contact with the alkene solution. This reaction is so effective that it is used as a test for the presence of a double bond in organic compounds. The mechanism of bromine addition involves the formation of a bromonium ion in the first step of the reaction. In the next step, a bromide anion is added, and the vicinal dibromo compound is formed. Notice that the bromide anion approaches the reaction site from the direction opposite to the bromine in the bromonium ion. Therefore, the halogenation of alkenes is usually a trans addition. For example, the bromination of cyclohexene produces 95% of trans 1,2-dibromocyclohexane. Halohydrins are compounds containing a halogen atom and a hydroxyl group at the vicinal carbon atoms. In the first step of the reaction, a halonium ion is formed, as in the case of reaction in a non-polar solvent. However, in the next step, a water molecule is attached to the halonium ion, with subsequent elimination of a hydrogen ion. Again, halohydrin formation is a stereospecific reaction and yields trans addition products. Cyclopentene reacts with bromine in a water solution to give trans 2-bromocyclopentanol. Hydrogen halide is added to the double bond in 2 steps. In the first step, the relatively loosely held pi electrons of the carbon-carbon double bond, which act as a nucleophile, are attracted to the electrophile. This forms a carbocation. In the next step, a halide anion is attached to the positively charged carbon atom to form a haloalkane. Hydrohalogenation requires the use of non-aqueous solvents, such as dichloromethane or ethanoic acid. Similarly, the addition of water is the reverse of alcohol dehydration. Water addition is catalyzed by acids. The first step of the reaction is again the formation of a carbocation. In the next step, a water molecule is added and a proton eliminated to yield the alcohol.
As you already know, the addition reaction of hydrogen chloride to ethene gives chloroethene. If we used but-1-ene instead of ethene, we could theoretically obtain 2 different products: 1-chlorobutane and 2-chlorobutane. However, analysis of the reaction products shows that over 99% of the product is 2-chlorobutane. The outcome of the reaction is illustrated by Markovnikov's rule. The outcome of the reaction is illustrated by Markovnikov's rule. During the addition of hydrogen chloride to the double bond between carbon-1 and carbon-2 in but-1-ene, the hydrogen atom from the hydrochloric acid molecule adds to carbon-1 because it has a larger number of hydrogen atoms than carbon-2. This explains why the major product is 2-chlorobutane and not 1-chlorobutane.
In the case of 2-methylpropene, the addition of hydrogen bromide may yield 2-bromo-2-methylpropane or 1-bromo-2-methylpropane. In accordance with Markovnikov's rule, the predominant product of the reaction is 2-bromo-2-methylpropane. Hydrogen adds to the carbon linked to 2 hydrogen atoms, while bromine adds to the carbon atom to which no hydrogen atoms are attached. In the case of 1-methylcyclopentene, we could theoretically obtain 1-bromo-1-methylcyclopentane and 1-bromo-2-methylcyclopentane. However, in accordance with Markovnikov's rule, the predominant product is 1-bromo-1-methylcyclopentane. The mechanism of the addition of a hydrogen chloride molecule to butene, like any other reaction of this type, consists of 2 steps. The first step involves interaction between the HX molecule and an electron pair, with formation of a new carbon-hydrogen bond. The arrow indicates the splitting of the pi bond in the alkene. Pi electrons form a new bond to the hydrogen atom of the hydrogen halide molecule. The second arrow indicates the breaking of the polar bond in the hydrochloric acid molecule, the electron pair staying with the chlorine atom. Thus, a chloride ion and a secondary carbocation are formed. The unstable carbocation very quickly reacts with the chloride ion to form a carbon-chlorine bond. The arrow indicates the electron pair of chlorine which forms that bond. Let us study the energy diagram for the reaction. The slowest step, which determines the rate of the entire reaction, is the formation of a secondary carbocation. The carbocation has the lowest energy between the first and the second step. The carbocation produced immediately reacts with the chlorine anion to form the final reaction product. The energy level of 2-chlorobutane is lower than the energy of butene and hydrochloric acid. Heat is released during the process, so the reaction is exothermic.
Tertiary carbocations have been experimentally found to be the most stable. Their formation requires the lowest activation energy. A secondary carbocation is less stable than a tertiary, but more stable than a primary carbocation. The methyl carbocation is the least stable of all carbocations.
Therefore, the formation of 2-chlorobutane from butanene arises from the higher stability of a secondary carbocation compared to a primary carbocation, which would have to be formed if 1-chlorobutane was to be produced. Given the relative stability of the individual carbocations, we can predict the products of any given addition reaction. Let us now try to arrange the following carbocations in order of their increasing stability, that is, the increasing ease of their formation. The least stable is the primary carbocation, with the next being the secondary one. The carbocation formed most readily is tertiary, and as such, it is the most stable one. Its formation requires the smallest amount of energy.
The products of electrophilic addition do not always follow Markovnikov's rule. This anomaly arises from the existence of 2 mechanisms for the reaction, leading to different products. One is the ionic mechanism previously described, which yields products consistent with Markovnikov's rule. The other mechanism occurs in the presence of peroxides or free radical initiators and yields products inconsistent with Markovnikov's rule. Let us study the mechanism of a reaction involving free radicals. Peroxides undergo thermal decomposition to give free radicals, which then react with hydrogen bromide. The reaction can occur in two ways. The formation of bromine atoms is energetically favorable. Bromine atoms initiate the energy-releasing process of the free radical addition of hydrogen bromide. The reaction products depend on which end of the double bond is attacked by the bromine atom. This is in turn determined by the stability of the alkyl radicals thus formed. Their stability, and consequently their ease of formation, have been shown to increase from the methyl radical through primary and secondary to tertiary radicals. Of the two possible radicals which can form in this reaction, the 1-bromo-2-propyl radical is the more stable one. The product of free radical addition is 1-bromopropane. If the reaction occurred according to the ionic mechanism, the product would be, in accordance with Markovnikov's rule, 2-bromopropane. Let us consider the electrophilic addition of hydrogen bromide to methyl cyclopropene, both in the presence and the absence of peroxides. The product of the ionic reaction is consistent with Markovnikov's rule. The reaction yields 1-bromo-1-methyl cyclopropane. In the presence of peroxides, the reaction occurs according to a free radical mechanism. The hydrogen atom of the hydrogen bromide molecule adds to the less hydrogenated carbon atom at the double bond. That is, the carbon to which a methyl group is attached. The product formed is 1-bromo-2-methyl cyclopropane, consistent with the anti-Markovnikov rule.
Now we can see the contrast between the two ways that hydrobromic acid, also known as hydrogen bromide, can add to an alkene. In the absence of peroxides, a proton is a reagent that attacks the double bond first. Because of the small size of a proton, steric effects are unimportant. It attaches itself to a carbon atom by an ionic mechanism so as to form the more stable carbocation. The result is Markovnikov addition. In the presence of peroxides, the larger bromine atom is the reagent that attacks the double bond first. It attaches itself to the less hindered carbon atom by a radical mechanism, so as to form the more stable radical intermediate. The result is anti-Markovnikov addition.